In order to prepare for exam 2, you need to study lecture 1 to lecture 5. Lecture 1, soil names and properties. Lecture 2, grain size analysis. Lecture 3, soil index properties. Lecture 4, soil classification. And lecture 5, weight and volume relationships in soil. In lecture 1, we reviewed different names and general properties for different names. We talked about 4 main categories for soil. The first one was when we have a combination of gravel and sand, which is called granular or cohesionless soil. These are particles larger than sieve number 4. The second name or category is silty soil, which is on the border between clayey and sandy soils. Then another group or category that we have is clay or cohesive soils. And finally, when we have organic soil. Then we talked about what is provided by USCS. So based on USCS and based on size, we can divide soil samples into 2 categories of coarse-grained soil and fine-grained soil. Based on USCS, particles retained on sieve number 200, which means that larger than 0.075 millimeters are coarse material, and materials passing through sieve number 200, which means that they're smaller than 0.075 millimeters, are considered fine particles, and then we have fine grain soil. Then if we look at coarse-grained soil, the particles can be divided to gravel and sand. Again, we can look at the size. So particles larger than 4.75 millimeters are considered gravel, and smaller than 4.75 millimeters, that's sand. Based on USCS, fine-grained is a combination of silt and clay. There is no size separation between silt and clay. What is important here is plasticity. Silt is usually low plasticity. There is no cohesion between the particles. Clay is when we have cohesion between the particles, they stick together, and it has high plasticity. In lecture 2, we went over grain size analysis, which means that we try to make this distribution curve which shows percent passing or percent finer from different size, which we also call it grain diameter, opening size, but it's basically how much material is passing through these opening sizes, or what is the percentage of particles finer than a certain grain diameter. So we have the opening size here, and we have the corresponding sieve sizes here. So what separates fine from, this is fine, this is coarse, from each other is sieve number 200. And as we mentioned earlier, this is sand, this is gravel, and this is sieve number 4. So here we have 4.75 millimeters, and here we have 0.075 millimeters. So the objective of sieve analysis and hydrometer test, or in general grain size analysis, is to make the grain size distribution curve. Because property of soil is influenced by the size of the particles and by how much of each size we have. So the distribution of grain size throughout the soil mass. So for fine material, fine grained soil, we do hydrometer test. For coarse material, we do sieve analysis. So you need to know what is the objective, how we do the test, and you need to be familiar with all the required calculations. So if you remember, we select a set of sieves. The coarsest sieve on top, the finest sieve here. Then we put our soil sample, we shake sieves, and we do the calculation to get our gradation curve or grain size distribution curve, which shows percentage passing of particles from each one of these sieves. So each data point is percentage passing from a sieve. Then from this curve, you need to be able to find D10. So you start from here, go to your curve, and this is D10. D30, start from 30% passing. That's your D30. And D60. This is our D60. Then calculate coefficient of uniformity, which is equal to D60 divided by D10. Calculate coefficient of curvature, which is D30 to the power of 2 divided by D60 times D10. And then use the statements provided in your lecture notes to determine if that sample is a poorly graded sample or if it's a well-graded sample. Also, you need to be able to calculate the amount of gravel, sand, and fines in a soil sample from sieve analysis results. So we select our sieves. Then we measure weight of sieves when they are empty. Then stack them on top of each other, put our soil sample in there, shake it, and then measure weight of sieves with particles retained on each sieve. Subtract those two numbers from each other and you have weight retained. Then you need to calculate total weight by adding all of these together. That will give you total weight of your soil sample. Then you divide each one of these numbers by the total weight and you calculate weight retained percentage. Then you need to calculate cumulative retained percentage. And finally, you need to calculate percent passing or weight passing from each sieve. Then you need to use these two columns. Opening size is our x-axis and percent passing is our y-axis. And you can make your grain size distribution curve. Make sure that you know how to do the calculations for these 4 columns. So in your exam, I may give you the table, remove these numbers, and then ask you to calculate them. You should know how to do the calculation for the numbers in any of these 4 columns. These are the statements that you can use to determine if a soil sample is well graded or if it's poorly graded. It's well graded if for gravel Cu is larger than 4 and Cc is between 1 to 3. If it's a sand sample, Cu larger than 6 and a Cc between 1 to 3. In class, we went over particle size classifications provided by 4 different organizations: MIT, USDA, ASHTO, and USCS. So this is the one that we usually use, but other organizations also provide these limits. So this is important because these are the limits that you need to use to calculate percentage of gravel, sand, and fines. That's when we are using USCS, or the numbers for percent of sand, gravel, silt, and clay if we are using any of these 3 organizations. And remember, for example, percentage of gravel is equal to percent passing from 76.2 minus percent passing from sieve that has opening of 4.75. Upper limit, lower limit. Percent passing from this one minus percent passing from 4.75, which is sieve number 4. And this is 3 inches. Or percent of sand is percent passing from upper limit minus percent passing from lower limit. So it's percent passing from sieve number 4 minus percent passing from sieve number 200. And the amount of fines is equal to percent passing from sieve number 200. In the next lecture, we looked at plasticity, soil plasticity, and we defined 4 different states for a soil sample: liquid, plastic, semi-solid, and solid. And this is with an increase in water content. And then we looked at the limit between these states. And we defined the limit, the water content at which soil changes from liquid to plastic as liquid limit. Water content at which soil passes from plastic to semi-solid, plastic limit. And then finally, water content at which soil changes from a semi-solid material to a solid material. That's called shrinkage limit. Then using liquid limit and plastic limit, we can calculate plasticity index, which is the range. Within that range, soil is a plastic material. So the two tests that we went over them in our class was liquid limit and plastic limit tests. So you need to know what is the objective of each test, what is the test procedure. Also, you need to be familiar with the calculations for each of these tests. This is a side note. This is the formula, general formula to calculate water content or moisture content. Weight of water divided by weight of solids or dry soil. So if you remember, for liquid limit test, we used what was called a Casa Grande cup. You made a cut in the center of your cup, and there was a handle which you turned. Each time the cup was raised for 10 millimeters, and you were supposed to stop when we have a half-inch closure here. You needed to repeat the test at least 3 times, so you have 3 data points. As you can see, the x-axis is number of drops, and the y-axis is water content. So water content, number of drops, 3 data points. Then we fit a line to our data points, and then you can find liquid limit. So liquid limit is water content at which soil changes from liquid state to plastic state. How do we measure that? Based on ASTM, liquid limit is water content at 25 number of drops. So you can make this curve 10, 20, this is 20, this is 30, so this is 25 number of drops. You can draw a line and find water content at 25 number of drops. This is your liquid limit. Water content at 25 number of drops. But in order to be more accurate, we find the formula for the line that we fit to our data points. And then in this formula, you replace x with 25 and your y is your liquid limits. Okay. Then the next test that we went over was plastic limit test. So plastic limit is water content at which soil changes from a plastic state to a semi-solid state. How do we find that? Based on ASTM, plastic limit is water content of a thread with diameter of 1/8 an inch where we see cracks. So you rolled your sample into a thread and took samples from the area that cracks are starting to appear and then calculated moisture content of that sample. In order to calculate moisture content, we use a small can. So we get an empty can. We measure weight of can when it's empty. So weight of empty can is 15 grams. Then we roll our sample and see cracks. Put some of that in our can. Now we have weight of can plus wet soil, which is 55 grams. Then we dry our sample, and then we have weight of can plus dry sample, which is 52 grams. So PL is water content, and it's equal to weight of water, which is 55 minus 52, divided by weight of dry sample, which is 52 minus 50. That's our plastic limit. In lecture 4, we went over soil classification. We again looked at unified soil classification system. There is another system provided by ASYN, and there is a soil classification provided in OSHA. So these are the letters that we can use. If we have a coarse-grained soil, then it's gravel or sand. If we have a fine-grained soil, then it's silt or clay. For gravel and sand, it can be well-graded, poorly graded, gravel with silt, or gravel with clay. For silt and clay, it can be silt with high plasticity or low plasticity, or clay with high plasticity or low plasticity. So the first thing that we need to do is to answer the question that do we have more than 50% fine particles or coarse particles. So in step 1, you look at percent passing from sieve number 200 to see if more than 50% is passing through or if more than 50% is retained on sieve number 200. Then you can answer the question and determine if you have a coarse-grained sample or a fine-grained sample. If it's a coarse grain, then it's mostly sand or gravel. If it's a fine grain, it's mostly silt or clay. That's step 1. Based on step 1, if we say that less than 50% is passing through sieve number 200, it means that more than 50% is retained on sieve number 200, which means that we have a coarse grained soil. If we have a coarse grained soil, now we need to see how much gravel we have in our coarse material. So you calculate percent of gravel and divide it by percent of coarse material. If this number is more than 50%, it means that we have more gravel. But if it's less than 50%, it means that our soil is mostly consisted of sand. So if it's gravel, then you need to follow this step. But if it's sand, then you need to go here. So step 1, step 2, and in step 3, we again look at percent passing from sieve number 200. If it's less than 5%, then we have clean gravel or clean sand. And you need to see if it's well graded or poorly graded. If we have more than 12% fines, then we have gravel with fines or sand with fines. And you need to use the plasticity chart to see if the fine we have is silt or clay. And if the amount of fines is between 5 to 12%, then you need to do both of these. So it's a dual symbol, and you need to determine if the sample is well graded or poorly graded. Also, you need to see if it's the fines that we have is silt or if it's clay. Now, if from step 1 we see that more than 50% of particles are smaller than sieve number 200, which means that we have a fine-grained soil. Now, in this case, what is important for us is plasticity of soil. So you need to look at plasticity or liquid limit. If it's less than 50%, we have low plasticity, we will use L. If it's more than 50%, we will use H. Then in step 3, you need to use plasticity chart to see if it's silt or if it's clay. Also, you need to answer the question if the soil contains, is it an inorganic material or not? So, for example, we have percent passing from sieve number 200 equals to 25%, and percent passing from sieve number 4 as 90%. So in step 1, we look at percent passing from number 200, which is 25%, which is less than 50%, which means that we have a coarse grain soil. Now that we have a coarse grain soil, we need to calculate the percent of gravel in our coarse material. So it's percent of gravel divided by percent of coarse material, which is 100 minus 90 divided by 100 minus 25. Which is equal to 13%, which is again lower than 50%, which means that it's mostly sand, not gravel. Now, we again need to look at percent passing from number 200, which was 25%, which is higher than 12%. So we have sand with fines. We need to use the plasticity chart to see the fines that we have in our sand sample. Is it clay or is it silt? Liquid limit is 45, which is here. And plasticity index is liquid limit minus plastic limit, which is 35, which is up here. So our point is above the A line. This is the A line. It's above the A line. And we can say that we have sandy soil that has clay. It's above A line and PI is higher than 7. I showed you this table, so you don't need to memorize anything, but this table provides a good presentation of different type of soil and which one is better with respect to drainage, with respect to workability, application for subgrade, or surfacing. We also looked at the classification provided by OSHA based on the structural classification. If we have granular soil with less than 15% fines with no plasticity, then it's basically just sand and gravel and it's type C. If we have granular with more than 15% silt and clay, but it has no plasticity, so it's granular, cohesionless. No plasticity means that it's mostly silt. Then it's considered type B. If we have clay or cohesive and more than 15%, then you need to look at unconfined compressive strength and environmental exposure conditions to see if it's type A, type B, or type C. But this is based on a decrease in stability. Highest strength, lowest strength. This is the highest. With a decrease in stability, we have a stable rock, type A, type B, and then type C. And in lecture 5, we looked at different formulas between weight and volume of soil. We said that we use a phase diagram which has a liquid, let's say air, gas, water, liquid, and the solid section. We have the total weight and total volume. We also have weight of solids, weight of water, weight of air, which is 0, volume of solids, volume of water, and volume of air. Volume of air plus volume of water is called volume of void. And then we have these formulas which provides a relation between weight and volume of soil and soil's component. Void ratio, volume of void divided by volume of solids. Porosity, volume of void divided by total volume. Degree of saturation, how much water we have in the voids, volume of water divided by volume of voids. Water content, weight of water divided by weight of solids. We have a moist unit weight, total weight divided by total volume. Again, this is called gamma. And we have a dry unit weight, or gamma D, which is weight of solids divided by total volume. A specific gravity is the ratio of unit weight of solids divided by unit weight of water. And remember, unit weight of water is weight of water divided by volume of water, which is equal to 62.4 pound per cubic feet. These three are specific gravity formulas. They're the same formula. Based on what parameter you need to use, you can select one of these formulas. And the next one was the relative density, which provides a description of soil denseness or looseness using dr, and this is just for granular soil. Okay, let's go over an example. We have 100% saturated soil that has a wet or moist unit weight of 112 pounds per cubic feet. So if we have a total volume of 1 cubic feet, then total weight is 112 pounds. Which means that total weight of solids plus weight of water is equal to 112 pounds. Then also the question tells us that this soil has a water content of 28%, and water content is weight of water divided by weight of solids. So we have weight of solid plus weight of water is 112 pounds. We also have weight of water divided by weight of solids is 0.28. Rearrange this one and we get weight of water is 0.28 times the weight of solids. We put this in here and we get weight of solids plus 0.28 weight of solids is equal to 1.28 weight of solids, and that's equal to 112 pounds. Now we can solve for weight of solids. That's equal to 112 divided by 1.28, which gives us 87.5 pound. And then weight of water is our total weight minus weight of solid, which is 112 minus 87.5, which gives us 24.5 pounds.